Welcome, this is Schweitzer, and this is a quick little lecture on, so the actual standard number here is going to be hashtag 4-1, 4-2 were liquids, and it would be A through C. So, again, this is why is a liquid a liquid? So these factors here are bunched into 4 dash to A. So the external factors are things that we as people can control, a liquid being a liquid. This is going to be temperature, which was discussed during solids, so that's where you want to go, and pressure. Pressure is starting to play an increased role in liquids, so we'll talk more about that here. The internal factors, why is a liquid be okay, on a bonding level, why is one molecule for some reason sticking together um, between between two molecules, why are they sticking together? So just a quick again preview of post view of this, because we already talked about that, and I'm not going to go through it again. For some reason, one molecule is attracted to another molecule. There's only one thing that causes attractions between molecules. That's partial negatives and partial positives. This attraction is called Coulomb's law. Force of an attraction is equal to the charge of the positive, the charge of the negative divided by the distance squared between. Again, there's small charges, but there are also small distances. So we get because we get so close. Some of these forces can become very strong. I would challenge you to take, a magnet, which has got a negative end and a positive end. Maybe this could be somewhat of a childhood, game. If you're messing with magnets, you have a positive and negative. Is attempt to see how close you can bring these two magnets together without letting them actually touch. At the beginning, it's quite easy, but when they start getting very, very close, the strength of the attraction is increasing uh, exponentially, and eventually it just snaps. You cannot keep them apart because the force is so strong. Same with molecules. These things are super close together, so the forces of attractions are very large. Anyways, these forces of attractions are called intermolecular forces, and we've already talked about them. And that's it for today on that thing. All right, so external factors. Um, so in this situation, um, all right, temperature and pressure. Now, again, this is the first part of this particular piece. Second part is properties of liquids. And you'll see that come up right after this on this video. So solids, we didn't really have a property of a solid. I guess you could say solids maintain their shape nicely. They don't form to a container, unlike liquids and gases. But liquids have a very unique property, which we use a lot, called solubility. So we'll take a little bit of a look here to see why why this property occurs. Liquids also will boil. So we will be taking a quick look also at that property. So this is what I would call standard 4-2B. And of course the C standard is the calculations. So it will actually quantify the solubility. Okay. All right, so more on pressure. Okay, so temperature, again, we already talked about, but make sure you understand temperature. Increase in the temperature will increase the movement of particles. This will put a strain on the intermolecular forces in which they're attempting to keep them together. So we take a solid and we start shaking them, and then all of a sudden they start breaking apart, and then they eventually break apart entirely. The molecule itself typically will stay intact. Okay. Another name for temperature, very important, is average kinetic energy. All right, what is pressure? Well, in physics, pressure literally is just force per area. So there's two types of pressure that we will deal with in chemistry. One is atmospheric pressure, and literally you are sitting in a solution of gases, and above you there's a constant weight pushing down on you of these things, the gravitational force. And anytime there's a high pressure, that would mean that those particles above you are heavier and therefore pushing down with a larger force than if it was a low pressure. A low pressure is, and if you watch the weather, you would hear all those things about highs and low pressures. You would realize, oh, okay, we have a high pressure coming through, and okay, versus a low pressure. You would associate high pressures with sunny and this with rain. Okay. The main reason for that, not to get into a conversation of weather, is that you pretty much have the same number of particles above you all the time. Our atmosphere is pretty, thickness is pretty much the same, unless of course you go up onto a mountain. As long as you haven't gone up in elevation, then the number of particles is the same. But if you're sunny, you have less water. And in this case, just plain gas. Most of the gases we have are N2. So that is 28 grams per mole. Whereas water, if some of those particles are being displaced by water molecules, well, water molecules are much lighter, and they're only 18 grams per mole, or AMUs per atom. So literally, if you have a lot of water above you, the physical force of gravity on you is less. Okay? And of course, as mentioned here in this picture, if you were to go up to a higher altitude, okay, and stand there, well, there's much less pressure here. Well, why is there less pressure? Because literally there's less air above you pushing down on you. Yeah. So, all right. So, how was this idea of pressure ever even figured out? Well, so in the, I would say ancient times, but a long time ago, Galileo was sort of given the question that people were having problems with why they could only pump water up so high. Okay, so people were using hand pumps and pumping water out of wells up, you know, to certain heights, and eventually they only pump it so high, and then they just could, no matter how hard you pumped this lever, it would never go any higher. And he didn't apparently want to deal with this problem, so he bumped it off to a guy. His name is Torricelli. And he did a lot of work with this stuff and found out that you're not actually pushing anything. What you are is, let's go to our previous picture again. All you're doing is creating like a void in where all the particles are now gone, and then wait for the pressure of the atmosphere to refill that spot. So they essentially create a low spot, and then the pressure of the atmosphere pushes it back. A good example of this might be literally just how you suck liquids through a straw, right? So you have your body, and let's say your head here, your chest cavity. You literally inside of your chest cavity will create a void or a little bit of a vacuum. Okay, a low pressure, and then the pressure of the atmosphere is pushing down. Will push down that. So when you suck through a straw, okay, then this particular what happens is that the atmospheric pressure pushes down on the liquid and pushes that liquid up the straw and up back into here. Yeah, and then you drink. That's all there is to it. So the way Torricelli figured this out um, was he created a little device, which you'll see to the left here. Okay, 1 second. All right, so what he did was he inverted mercury into a tube. And one of the things they were very good at this time of history is making glass stuff. You might think that'd be kind of hard now, but back then that's was very very common. So they filled it all the he filled it all the way up to the top with mercury, inverted it into a pool of mercury, and he waited for this thing to see what happened. I'm assuming he started relatively small, and then it wouldn't slouch, would just stay there. I mean, that's what I would do. I mean, if you're trying to do an experiment, you start small and you get bigger, and didn't slouch. It didn't slouch and it just stayed full. Sometimes I'll pose the question to students. Sometimes you can, if you're drinking a soda from McDonald's, and you can take soda, you can suck it up into a straw, and you can put your thumb over this particular area and or finger, and the soda stays. Okay, so some might make the question. Torricelli made this very question. Okay, if your finger keeps the liquid there, how would it keep it there if there were two straws? Could you do it with two straws and fill it up with liquid and then hold your finger there? Could you do it with three straws? I mean, at some point, is this just an infinite property and you can go on forever? Well, it turns out that there's things don't happen for no reason at all. We have a balanced forces here. At the force of atmosphere pushing down and the force of gravity pushing down as well on a bit of a seesaw. This is gravity, and this is atmospheric pressure. And at some point, if you put your finger over it, the reason why it stays there is because the force of the atmospheric pressure is greater than the force of gravity. And in fact, that's how it got there to begin with. The only reason the water's up there is because we created a low spot and the atmospheric pressure pushed it up. There is no such thing as suction. No such thing as suction, just difference of pressure. Another common example of kids when they're younger, and you might be one of these here, where you will take a crude looking face, all right, and put a glass jar over your mouth and start sucking the air out. You create a low spot here, and all you're feeling at that point, you really get to feel the atmospheric pressure pushing down on your face. So essentially, Torricelli used mercury. Mercury happens to be 13 times more dense than water, and at that point, it only required 76 millimeters. So that's close to a meter. So think of it in terms of almost a yard, like part of a yard, most of a yard. So that's a decent length, and it always stayed here. This became a vacuum. There's nothing here. So in this case, as days would go by, this liquid would go up and down. So now we use a unit of pressure that is an equivalent to a unit of millimeters of mercury. So millimeters of mercury, this is something that kids use millimeters of mercury all the time. as a standard unit of pressure, but I don't think that they really understand how that is. It's just a number to them. But essentially, 760 millimeters of mercury is the amount of mass or weight needed to counterbalance the atmosphere. So on one side you have, let's see here, you have a little tube of mercury. It's very short. And then you're comparing it to an entire column of air above it. The air is not very dense. So the weight of mercury in this tube is equivalent to the weight of all the air of the column. Either way, it's a unit of pressure. Okay, 760 millimeters of mercury is equivalent to what we now use, somewhat more common, is atmospheres. 1 atmospheres, ATM. Okay, this is also, because Torres Light did it, he named it after himself as a torr. Okay, those are equivalent. This is believe this would be in your laminated sheet. Okay, so pressure is force per area. Now I will mention one more thing, is that, as I kind of alluded to this earlier, and let's see this next time. I'm going to drop a slide in here. There are 2 different types of ways we'll measure pressure in chemistry. And one of them is obviously with atmospheric pressure. We use this all the time with like a flexible container like a balloon. So we have a pressure inside, we have a pressure outside, and if the balloon's not expanding or contracting, then these 2 pressures are equal. Okay, but we also could take a rigid container, one that's not flexing. Now we have particles inside of this container that are moving and slamming off the inside container of this inside wall of the container. This is also happening in this container. So quite often we're looking at pressure inside of containers. Only reason why I have a pressure inside of this container or this container is an accumulation of collisions colliding with the inside container of the wall. All right, so and that factor will come up more during gases. Why would we get more or less pressure? Well, you just have more or less collisions, or you have more forceful collisions if it's a heavier particle. So keep in mind that we have atmospheric pressure, sure, but we also have pressure inside of containers. So I could have a pressure inside of this container of 760 millimeters of Hg. All right, well, what does that mean? Well, that means that this overall force inside the container is equivalent to the same force that a column of mercury, 760 millimeters of mercury would produce, and I guess also equivalent to a column of air. The same amount of weight, force pushed down. The force at the bottom would be the same as that force inside there. So, you also would note that if you have 1 atmosphere of pressure out here on a flexible container, you have 1 atmosphere of pressure here. Well, then the balloon doesn't go anywhere because the same pressure on both sides. So it's balanced. All right. So again, pressure is force per area. Pressure is directly related to the number of collisions with the particles on the inside container of the wall. This is an important little phrase. Okay. All right, so here's 2 example containers, and we're just starting to introduce this idea of what's called vapor pressure. Okay, any liquid, I would say, that if you cap it, happen to have water molecules here, but if you cap it, you're going to have water particles sort of escaping from this liquid. Now, this does not continue on infinitely, because if it did, you'd have more and more and more and more and more particles in here. And then, of course, as I've just mentioned, the more collisions we have with the inside container of the wall, the more pressure we have. So in this situation, of course, we know that just from daily, everyday experiences, we don't have containers in our refrigerators that pressure is just keeping building and building and building and building. So it turns out that we form a bit of a balance where as things leave, they also re-enter. And inherent to the very particles themselves, we reach a balance called equilibrium. Okay, and this is going to be a very important topic coming forward. But for a given temperature, we feel we have a certain amount exiting, a certain amount entering, and we have with a certain what's called vapor pressure. Okay. All right. So if I warm this thing, okay, turns out that we get more particles in here. You might maybe realize this. That okay, as I warm it, I'm going to have more particles in here. But then again, if I come to a new temperature, I get a new vapor pressure. It happens to be higher. Okay. So what do we want to know about this thing? Well, it turns out that the intermolecular attractions between these particles can't change it. I cannot change unless I change the particles themselves. They have inherent intermolecular attractions. Turns out that the more intermolecular attractions you have, the more they're going to stick to themselves, and the less likely they're going to want to jump off the surface. Or it's going to take more energy to get them to jump off the surface. So, for a given temperature, we have less particles up here for higher attractive substances. And we call, so here's the trend. Increased intermolecular forces means decreased vapor pressure. That's important. You're going to see that. I also would mention that if you increase your temperature, you're going to have increased vapor pressure because the particles are moving faster. A certain amount of energy is required to break them away. And if you raise the temperature, more of the particles have that energy. All right. This particular chart is looking at the relationship between pressure and temperature. Isn't something that we'll do a lot in chemistry in this class, but I've mentioned it in the solids video. Solids, liquids, and gases. This is the point where all three are present at once, called the triple point. This is referred to as the melting line. This is the vapor line of vaporization and line of sublimation. Can't be held as a liquid anymore, just too hot. Again, at normal pressure here, we would come across, and this substance here at 1 atmosphere isn't even going to boil, it's going to sublimate. So typically, at a higher pressure, this thing would have both a liquid phase, melting point, and it would have a boiling point. So, one thing is quite always been a bit perplexing to me is that when you look up in the sky and you have clouds, okay, and those clouds are they're gases. Like, why don't they just turn to liquid? Well, just because things that happen at our level at 1 atmosphere aren't necessarily going to work up there. As I reduce my pressure, I'm dropping. This is not for water, but it could be very similar. I'm dropping down, and now it doesn't go. There's no liquid state. It goes from a solid right to a gas, or it could just be a gas, and again, it could form a solid and fall. It's not working the same. And you can imagine a planet where there's much less atmosphere. That liquid's just much less atmosphere, so much less pressure, and therefore just no gases, no liquids occur. Or you could be on a planet that's so massive that the pressure is so high that everything just becomes a solid. Gases are difficult to have unless temperature's super high. So, I mean, it's unusual. This question's saying what happens when we go from at normal pressure, which is 1, from negative 100 to 30. So we're going to have sublimation. Okay. The critical point of carbon dioxide is 304 and 73. Under which conditions is carbon dioxide a liquid? All right, so this is this guy here. So I would want, if this is 73 and 304, as far as conditions are concerned, pressure. So it says the critical point of carbon dioxide is 304 and 73. Now this is not carbon dioxide's drawing. I just put this on here. So this would be, here would be 304. And this would be 72, 73. Okay, now what's great about this particular question is that it gets you realizing that, okay, as I increase my temperature, things start moving towards liquids and then towards gases. As I increase my pressure, things are moving towards being solids, because that's what's going to do to it. So it says, what conditions would it be a liquid? So I would want to have, okay, critical point. This is the highest temperature which a liquid could be consumed, could be. So I would want to have increased pressure and decreased temperature. So decreasing the temperature, same, okay. This would work here, I think, because at a given pressure, this is the highest temperature that a liquid could be maintained, or at this temperature, a liquid can no longer be established. All right, so essentially we would be moving temperature-wise from this point here into the liquid phase. So I think that's a yes. All right, so 305 and 74. Okay, so I've moved above the 304, so I don't think a liquid can be maintained anymore regardless of pressure. So I would go with 1 only. Okay. All right. So properties of liquids. This is going to be, we're considering so in this situation, we always want to be looking at, why do things dissolve, and then that could be something that could be involved in bonding as well, but what are the factors that allow something to dissolve better? Okay, how can we control the way at which things dissolve? What can we do to affect that? So, anyways, so first of all, whenever you're dealing with why things dissolve, is because in the particular solution, for whatever reason, there is an attraction between the solvent and the solute. We'll call this guy the solvent. There is no difference between the solvent and the solute. The only difference really is typically the solvent's in larger quantity. So water is a typical solvent, but can we dissolve water and other things? Absolutely. But anyways, there's got to be some attraction between these guys. And whenever you're trying to justify solubility, you must justify it in terms of typically some sort of force. They could be any of these guys here. Ion dipole tends to be pretty common because the ion compounds dissolve fairly nicely. So you'd have to have a charged particle, and there's a picture here showing an ion dipole. Okay. But again, we've talked about all these things, and you're going to want to be comfortable with these things and recognizing them and saying, yeah, this thing will dissolve because it has lots of these intermolecular forces. You can have a London dispersion force as well, but that would be called an induced dipole, which isn't as common. But so again, what are the factors that we can control? Well, the only ones we have control over is temperature and pressure. So you will find very little, I don't know, you'll find come with some reason in your own, I guess, but you'll find very little written in books as to why you increase temperature, you increase the solubility of a solid dissolving in a liquid. That's true. So if you want to dissolve, let's say, for example, table salt into sugar, okay, table salt into water. So you'd have to have some Na plus ions, some Cl minus ions. And if you tasted this thing, it would taste salty. Add more salt and it gets saltier. But eventually there's solid salt in the bottom and you're not going to get any saltier of a taste. Okay. And I would also suggest that if you ever do that, it's not really good to drink that salty of water. I'm fairly certain if you drink a cup of completely saturated salt water, there's a good chance you could have some health problems immediately, very soon after. Because your body is just one big salt solution, and your kidneys would be going nuts, and your body would not like that one bit. So it could be very problematic. All right. So, anyways, on a side note, then, the only way to get saltier would be to raise the temperature. All right. Now, gases, for whatever reason, are just the opposite. Again, I don't particularly know why this is. Again, I could postulate about what might be happening on a molecular level, but essentially, at this point, if I have a liquid and I want gases to dissolve in that liquid, it works better at colder temperatures. Okay, this is pretty easy to realize for like something like a soda. You know, cold soda dissolves gases very nice. And when you drink a soda, it warms and then the gases are released, which is why it feels bubbly in your throat. So, all right, well, what about pressure? Okay, so I'm going to clear this out just to give myself a little more room. All right, so first of all, solid dissolving in a liquid, pressure-wise, doesn't really have any effect. So if I have NaCl dissolved in a liquid, okay, and say I have solid here, and the solid's on the bottom, so it's saturated, that maximum solubility. If I were to put this in a situation where I increase the pressure, atmospheric pressure, or put it in a pressure box or some other area, it's not going to cause more to dissolve or at least not anything noticeable. So pressure doesn't really have any effect on solids dissolving. It does, however, have a large effect on gases dissolving. This is seen very nicely in a soda. So sodas are carbonated beverages. Okay, so there's a small space above here, and you have a very large amount of carbon dioxide that is staying in the soda very nicely. Okay, only because you have a large pressure above this thing. And this, at this point could be considered the vapor pressure of carbon dioxide. Gases leave, gases enter. And it has no problem maintaining its solubility as long as you have such increased pressure. All right? And then at that point, as soon as you open this container, all right, and allow this gases to escape, all right, well, that will work. Now, with this situation, what happens? Well, it doesn't happen immediately. It takes a little bit of time, okay? But there's no more gases, very much gases, re-entering the thing because they all escaped, okay? But gases are still exiting the solution, and they bubble out at a specific rate, and eventually they'll get to a new balance. Does all the carbon dioxide ever leave the solution? No. It becomes in balance with the atmosphere. The atmosphere has carbon dioxide in it. So again, there is still gas of carbon dioxide re-entering the solution, just at a much slower rate. So the normal carbon dioxide that's in the air will re-enter the solution, and the other stuff will exit, and eventually we'll get a composition of carbon dioxide in the solution, all right, that is very consistent with what's in the atmosphere. You'll have a similar concentration of carbon dioxide in the solution that's that of the atmosphere. And of course, other gases too, like nitrogen and any other gases that are present will come and go and form similar ratios to that of the concentrations in the atmosphere. Important thing is, why do things dissolve? Because of intermolecular attractions. What are things that we can control? Temperature and pressure. Okay. Again, kind of covered this already. How do we get more stuff to dissolve? Well, if you want to dissolve a solid, the only thing you can do is increase the temperature. If I wanted to get gases to dissolve, I got to increase the pressure on the top of it, of that particular gas. Okay. So if I want to get carbon dioxide to dissolve better, I need carbon dioxide pushing down on top of this thing and lowering the temperature. Sample question. At 50 degrees Celsius, a 50-gram sample of ammonium chloride is added to 100 milliliters of water and stirred. Which of the following is true? Take a moment, and what do we think? Okay, so first of all, this substance is ionic. It will produce ammonium ions, and it will produce chloride ions. So the answer is yes. It will be an electrolyte because there's ions present in the solution. The solution is considered saturated. Okay, well, let's figure this is a solubility curve. Okay, again, as temperature increases, so does the solubility. Now, some things increase more than others. Looks like this chemical actually gets less as temperature goes up. That would be an anomaly. All right, so there's ammonium chloride, and okay, 50-gram sample, so a little less than 1 mole. So let's do the actual, what do we actually have here? I have a little bit less than 1 mole. That's in 100 milliliters. So 0.1. So that's not a decimal there. It's a little less than 1 mole. So we have a molarity that's a little bit, to me it would appear a little bit less than 10. Either way, so that's one example. We could actually calculate the actual number of moles. It's very close to 1. Okay. Anyways, let's see what we got here. So we're at 50 degrees. Come up here. We call this, I guess you'd call this like a direct read. Right to here and cut across. So we didn't really need the molarity, but just kind of a side note, I guess. It's saying that in this situation, at 50 degrees Celsius, 50 grams of this stuff can dissolve. And yeah, that's pretty, as far as I can tell, that's smack on. So are we saturated? It's gonna be real close. Like, we're full. The solution has a concentration of less than 1 molar. All right. What did this thing here? We're less than 10. Okay, so this would be no. All right, so that's the reason why I did this here earlier, I guess. But we have 1 mole in. If we had 1 mole in 1 liter, we'd have 1 molar. I got 1 mole in a tenth of a mole of a liter, so we're like 10 moles per liter. All right, this is now moving into compositions of liquids. One more thing I want to add in here that I didn't add, that we'll add right now, is why do things boil? Now again, this could be added in gases. Like, why do gases boil? What you could look at in terms of the liquid boiling, or you could look in terms of the solid boiling. The gas condensing. But I'm going to add it in right here just so we have this here. Okay, so one property of liquids is why do liquids boil? And we'll kind of talk about that momentarily. Why do liquids boil. Okay, so in this situation, just so we know that the phenomenon that occurs that allows things to boil is that the vapor pressure, so if we have a container here, all right, that's got some liquid in it, okay. Why would this thing boil? Well, we know we have a vapor pressure, okay, producing liquids or gases above this thing. Well, and we know that when the vapor pressure increases, is result of the temperature increasing. So, and at certain temperature, it boils. What's happening here is the vapor pressure, as it goes up, it gets awfully close to the atmospheric pressure. And when the vapor pressure exceeds the atmospheric pressure, bingo, boiling occurs. So there is two ways in which you could boil something. One, you can raise the temperature up until the vapor pressure exceeds atmospheric pressure. Or you could maybe go someplace or create an environment in a container or whatever that the exterior pressure would drop. We've done this in vacuum chambers where you take and suck all the air out, and you can get a number of things happen. One is if I take all the air out of this particular thing, and let's say I have some soda in here, some immediately as I remove any amount of pressure, all of the gases inside the liquid escape. Okay, because there's nothing holding them in. There's zero re-entering and they're just exiting. It boils it looks like it's boiling, but just gases in there are escaping. And then two, you keep on going, and you will see the actual liquid itself start to boil. And it's not hot. It's just boiling at a lower temperature. You should be aware that if you go up to a mountaintop someplace and you try to cook food, water will boil at 96 degrees, maybe at a higher altitude, than it would at down here. It boils at 100 degrees Celsius. Well, why is the difference? It just requires less temperature to get. You don't have to get the temperature quite as high because it doesn't have as much atmosphere to get over. So I don't have the vapor pressure as high as I would normally need to at a lower atmosphere. So one kind of peculiar thing, again, kids don't always realize these things. As we go forward, we'll be using vapor pressure of water, pretty commonly in some of our labs and things we'll do. Okay, so typical vapor pressure of water. You could Google vapor pressure of water. In fact, I think we might as well do that. So let's go ahead and do this. All right. Got my trusty periodic table here. All right, let's just grab this guy and type in vapor pressure of water. Okay. There we go. Pull it up, and let's go with images. We'll get a chart of vapor pressures. And let's see, they want to do some stuff here. All right, this one looks good. All right. Now, a couple things you notice about this particular guy here. All right, first of all, as the temperature gets higher, what happens to the vapor pressure? There's a chart like this in your lab book. You'll eventually get a lab book if you don't have one. It's in it. Well, usually include the lab book. But anyways, it gets higher. Okay. So this means that at higher temperatures, if we leave a container of water just sitting here, okay, and we cap it, all right, put some water. Doesn't matter how much water is in there. There's a little bit of water. It's always got to be some water there. That the amount of pressure of gas particles in here is going to reach this particular pressure at that temperature. So pretty low pressure. If remember, 760 torr is 1 atmosphere. So relatively low pressure. But you notice it gets bigger and bigger as you warm. And then as we go all the way over, now this one stops at 31. It's already up to 33 millimeters of mercury. So I'm going to back up here and find a different chart. Let's go here. All right, so most of the charts go up a little higher. Let's find one that goes a little higher. Here we go. All right. And let's zoom in. Now, as we look closely at this thing, we get temperature. Okay, now, again, this is giving it to us in pressure, and pressures, and must look like it's something unique. Must be per square inch. I don't want that one. Oh, all right, I know this would be so difficult. All right, so let's go to a different one. Let's try this one. All right. All right, so this one goes all the way up to 99 degrees. All right, so close enough. Big waste of time here. All right, so notice at 99 degrees, this pressure is right at 733.24 millimeters of mercury. Okay, at 100 it is 760. And that's the part I was hoping to show you, is that if you look on your chart, you will find that at 100 degrees Celsius, it is exactly 760. All right, and again, yeah, it's not going to show up here. All right, so either way, so that ends our video on this. Keep in mind that if we raised our temperature up to 100 degrees Celsius, what would be this pressure inside? It would be 760 millimeters of mercury, Hg, which happens to equal that of the atmosphere, which is why it boils at 100. Long story short. All right, thank you very much.